Hello, welcome to lecture 23 of the course. We have covered almost all the essential concepts of quantum optics in our previous lectures. In these lectures and in the next couple of lectures, we are going to discuss about some very important applications of quantum optics. In particular, we are going to discuss about the so-called superconducting circuits, also known as circuit QED platform. Apart from circuit QED, we are also going to discuss about optomechanics, quantum optomechanics, which has immense technological applications in quantum technology. In these lectures, we'll begin with discussion of superconducting circuits. So let's begin. Superconducting quantum circuits are the subject of intense research at present. These circuits are macroscopic in size, as I am showing you two figures related to superconducting quantum circuits here. As you can see, these are macroscopic in size but have generic quantum properties such as quantized energy levels, and they also exhibit superposition states, and finally, most importantly, quantum entanglement. And these are three properties which any typical quantum technology component or device has to exhibit: quantized energy level, superposition state, and quantum entanglement. And superconducting qubits form the key components of these circuits. Now, these superconducting qubits come into limelight recently due to its use in quantum computers, and these quantum computers, as announced by many major companies such as Google and IBM, are based on superconducting circuits. For example, as you can see here, these are prototype quantum computer by Google and IBM, and both of these quantum computers are based on superconducting circuits. As you can see, because of the fact that superconducting circuits is based on qubits, superconducting qubits, ultimately in terms of physics, superconducting qubits being a two-level system, it's all about exploration of quantum optics in two-level system. While the knowledge of superconductivity is not required, however, having a bit of basic knowledge of superconductivity always helps. Now we all know that metals and insulators, we know all about them, right? Metals and insulators. Insulators are bad conductors of current or electricity. Metals are good conductors. On the other hand, superconductors, as the name says, exhibit zero electrical resistance, that is, allow current to flow without loss. However, a superconductor can do so below a critical temperature only. Probably most of you are familiar with this plot, electrical resistivity versus temperature plot. Here, as you see, in a usual metal, the resistivity decreases. Okay, it decreases as temperature is reduced, but it does not drop down to zero. Even at zero temperature, it has some finite resistivity. However, in the case of superconductor, resistance suddenly drops. For example, here at a particular temperature known as the critical temperature, the resistivity or the resistance suddenly drops to zero at Tc, and this phenomena of superconductivity was discovered by Heinke Kamerlingh Onnes in 1911, which earned him a physics Nobel Prize in 1913. Now, one of the most important property of a superconductor is that it shows what is called Meissner effect. Actually, what it means is that a superconductor shows perfect diamagnetism. So it was found by Walter Meissner and Robert Ossenfeld in 1933 that a superconductor expels externally applied magnetic field below the critical temperature, as you can see from this plot, and this is also the reason why a magnet is levitated in a superconductor. Now, a superconductor is typically characterized by three parameters that describe the external conditions necessary for a metal to be superconducting, and these critical parameters are firstly the so-called critical temperature called Tc. That means the material to be a superconductor has to be cool below the critical temperature Tc, which is mostly in the range of 0 to 20 Kelvin for low temperature superconductors. And another parameter is the so-called critical magnetic field SC. Now, the strength of the magnetic field surrounding the superconductor must be below a certain point known as the critical magnetic field SC. Okay, and as you can see here, the superconductor, from this plot you can see that superconductor can expel magnetic field as long as the applied magnetic field H is less than this critical magnetic field, and this critical magnetic field is generally in the range of 0.1 to 10 Tesla. And another parameter of importance is the critical current. The electrical current passing through a metal must be below a critical current IC to be eligible to be called the metal as a superconductor. And since this critical current depends on the cross-sectional area of the metal, generally the most used parameter is the current density Jc, critical current density Jc, defined as critical current per unit cross-sectional area. And it is the most used parameter. Instead of critical current density is used, and typically it lies between in the range of 100 to 10,000, 10 to the power 4 ampere per millimeter square. All the mentioned three parameters are highly correlated and depends on each other. Now let me talk briefly about the so-called BCS theory. The BCS name come from the Bardeen Cooper Schrieffer. B for Bardeen, C for Cooper, and S for Schrieffer. This theory is of relevance to us, as you will see. This BCS theory explains the phenomena of low temperature superconductivity quite well. And according to BCS theory, which was put forward in 1957, resulting in 1972 Physics Nobel Prize, it basically says that the electrical conduction in a superconductor happens due to the formation of so-called Cooper pairs. And a Cooper pair is formed by two electrons glued to each other via the so-called phonon interaction. This Cooper pair can propagate through a superconducting lattice without any resistance. The formation of Cooper pair could be understood intuitively as follows. As you can see in this picture here, there is a superconducting lattice is there. By the way, all of you know that inside a metal, negative charge of the conduction electron is balanced by the positive charge of the ions that make up the crystal lattice. And this balance makes the total charge to be neutral on the average. We all know this. Now, on a very short time scale, an electron passing through the lattice of positive ions, if I am talking about a metal which is cool below the critical temperature, that means a superconductor, what happens there is that at a very very short time scale, an electron passing through the lattice of positive ions will pull the ions towards it. As you can see, as this electron is passing through this lattice, it has created a positive charge density in a region here, positive charge density, because while it passes through the lattice, it pulls down the ions towards it, creating this electron basically leaves a slightly positive charge density trail behind it. This region of positive charge can attract a second electron. As you can see here, this second electron is attracted by this positive charge region, and this will result in the attractive electron-electron interaction. The two electrons are correlated by lattice vibrations or deformation, also called phonons, and can give a separation of around 100 nanometer or so. As you can see now, these two electrons are correlated to each other, forming the so-called Cooper pair, and separation between them is on the order of 100 nanometer or more, which is much larger than the distance between ions in the lattice, which is typically on the order of 0.1 nanometer. For example, here in this plot I am showing you that the Cooper pairs are separated by 100 nanometer which is again formed due to the phonon interaction, and the lattice spacing is only on the order of 0.1 to 0.4 nanometer. And as you can see, the charge on a Cooper pair is equal to twice that of the charge of the electron. Now, because this Cooper pair is formed by two electrons, in order to break this Cooper pair, one needs to apply some energy, and this is responsible for the so-called band gap energy in a superconductor. And you know that in a typical metal, normal metal, the energy spectra looks like this. Here, as you can see, there is a continuum of energy is there. On the other hand, in a superconductor, because of the Cooper pair, there is a band gap, and this band gap is by convention is denoted by twice delta. So this band gap of energy is denoted by this symbol twice delta, and a superconductor can be in a ground state for a given number of Cooper pairs at absolute zero temperature, T is equal to 0. In fact, one of the most important prediction of the BCS theory is that it basically gives a relationship between the band gap energy at the absolute zero temperature to the critical temperature of the superconductor, and this relation is as this, that this band gap, that is twice delta at T is equal to 0, is related to Tc is equal to 7 by 2 or 3.5 into Kb. Kb is the Boltzmann's constant and Tc is the critical temperature. Now you have to note that this critical temperature is on the order of 1 Kelvin for all low temperature superconducting materials such as aluminum, niobidium, or alloys formed by these elements. Okay. Now at low temperature, that is below the critical temperature, one is a superconductor is typically always in a ground state for any given number of particles, and particle number, as you can see, can change by a factor of particle. This particle number can change by twice n, where n is the number of electrons, by twice n, because a Cooper pair always we have two electrons in it, right? So therefore particle numbers can change by amount to n, where n is the number of electrons. The BCS theory was able to find the complete form of the ground state wave function. The BCS ground state wave function describes a collection of globally phase coherent electrons. The quantum phase of each Cooper pair has a well-defined relation to each other. In this way, the Cooper pairs form a macroscopic quantum state known as BCS condensate. So this macroscopic quantum state is called BCS condensate. In fact, this BCS condensate is responsible for the immunity of the Cooper pairs for scattering at low temperatures, and this gives rise to perfect conductivity of superconducting phase. In fact, there is a theory put forward by Ginzburg and Landau who postulated that a single wave function describes the condensate of Cooper pairs. This theory explains many important macroscopic properties of superconductors, low temperature superconductors successfully. We will focus on some key elements of the theory which are relevant to us. Say psi of r is the superconducting wave function for the condensate. say this is the wave function for superconducting condensate, and here R is the position within the superconductor. So as per Ginzburg-Landau theory, it says that rho of R, let's say it denote the particle density or the Cooper pair density. This represents the density of Cooper pair, and this Cooper pair density is given by the square of the modulus of the wave function. That means it's basically psi star of R, psi of R. Okay, so therefore in terms of this particle density or Cooper pair density, we can rewrite this wave function psi of R in terms of rho as follows. We can write it as square root of rho of R. Because this wave function is a complex quantity, so it has a phase, and its phase is defined as theta R. Theta R is the phase of these Cooper pairs. Now we can interpret this Cooper pair density rho as the particle density, as it's the wave function of a large collection of Cooper pairs. This wave function psi of R satisfy the Schrodinger equation as usual, and this is the Schrodinger equation. Here this H is the Hamiltonian for a particle placed in an electromagnetic field, right? And you know that the Hamiltonian for a particle of charge q placed in an electromagnetic field is given by this expression. Here you have minus IH per delta minus q into A is the vector potential associated with the magnetic field, divided by twice m. So this is the mass of the condensate, m is the mass of the condensate, plus q charge into the scalar potential phi of R. Okay, so here, by the way, if you recall, this is basically P. If I say P is the momentum, then P is equal to, as you know, in 3 dimension, I can write it as IH bar delta. And because of the coupling of the charged particle to the magnetic field, then this part is also appearing here. So just to make you understand that this part basically refers to the fact that this is the kinetic energy term in a way, and this part represents the potential energy term, right? So this is the usual form of the Hamiltonian, as you know. Okay, now a very interesting and unique property of the superconductor is that the magnetic flux within a superconducting loop is quantized. So this is very important result. The magnetic flux within a superconductor or say superconducting loop, rather superconducting loop is quantized. This is one of the most important property, and this is utilized heavily in circuit quantum electrodynamics, and this is a consequence of the fact that superconducting condensate have a coherent global phase. Okay, now here the global phase in this equation is basically given by the theta of R. Okay, so this represents the global phase. This represents the global phase. This fact that magnetic flux within a superconducting loop is quantized is the building block of many superconducting qubit. To understand this quantization, let us consider a superconducting ring placed in a magnetic field B oriented perpendicular to the plane of the ring. you know what happens is that when the superconducting ring is placed in a magnetic field, the so-called Meissner effect is triggered, and this implies that a screening current, when this superconducting ring is placed in the magnetic field, a screening current is developed on the surface of the superconductor. That means a trapped current is generated on the surface of the superconductor that cancels the magnetic field in the bulk of the superconductor material. Since the current density is zero deep inside our superconducting ring, so deep inside the superconducting ring, in the diagram here, what you saw as the current is basically on the surface of the ring, okay, but deep inside the current density is equal to 0. So it follows that because we know the expression for the J is equal to h bar by m gradient of the global phase theta minus q by h bar into the vector potential A rho, and this is equal to 0. This implies that we must have gradient of theta is equal to q by h bar into the vector potential. Now let us take the line integral on both sides of this equation around a contour loop, say defined by say gamma. If I take this line integral on both sides, then this is what we are going to have: q by h bar a dot dl. Now if I apply the Stokes theorems on the right hand side of this equation, then we are going to get q by h bar. This, the Stokes theorem is associated with the fact that it converts a line integral into a surface integral. So we have this equation here, curl of A surface integral over the surface S, and curl of A is nothing but the magnetic field, so I can simply write it as q by h bar, and this is B dot ds. Again, as you know, this surface integral is nothing but the magnetic flux q by h bar into magnetic flux phi. Okay, so this is the magnetic flux. So what you are having now is that q by h bar into the magnetic flux is equal to this integral gradient of theta, line integral gradient of theta dl. Now if we evaluate the line integral on the right hand side between point 1 and point 2, then this line integral is going to give me the theta 2, the theta value at point 2 minus theta at point 1, that is theta 1. So it is clear that if we evaluate the integral over a closed contour, then it appears that this line integral should give me 0. Okay, should give us 0. However, one needs to be careful here because this result is valid if the fields are simply connected. That means in regions where there are no holes. So this result is okay for correct for simply connected region. That means the regions where there is no holes. However, as you know, in our case we are considering a superconducting ring, and that means we are in a multiply connected region, and that is a region where there is a hole. And so in this case the line integral need not necessarily go to 0. It may not be equal to 0 for a multiply connected region. Multiply connected region. Now you know from the fact that the wave function must be single valued, the superconducting wave function must be single valued, so we must have psi at theta 0 should be equal to psi at theta 0 if I come back to this point theta 0 by one contour or one trip or multiple trip, then I should always get it to be the same, because the wave function has to be single valued as demanded by the postulates of quantum mechanics. This equation basically means that if we start at the value theta 0, and once you make a return trip to this value theta 0 once or maybe multiple times, all the time you should get the same value. That means the phase can take only values this should be different from one another by integral multiple of 2 pi only. Okay, in fact this is quite evident from the fact that psi of r theta is equal to square root of rho e to the power I theta. So if I go by one cycle or multiple cycle, say theta plus 2 n pi, then you see immediately, because of this fact, these equations are automatically satisfied, because I am going to have here I theta plus 2 n pi, and you know that e to the power I to n pi is equal to 1. Alright, so therefore what we must have for multiply connected region, gradient of theta dot dl is equal to integral multiple of 2 pi. So this is a very important result. By dint of this result, we had on the left hand side q into the magnetic flux divided by h bar, and on the right hand side we had that integral. Now this integral is that line integral, as you have found, that it should be an integral multiple of twice pi. So from here we get the magnetic flux phi should be equal to, as you can see from this equation, it would be 2 pi h bar divided by q into n. Okay, and this I can denote this particular quantity, which is a constant. This is called flux quantum. I can denote it by phi 0 into n, because of the fact that charge q here is twice of the charge of the electron. So therefore this phi 0 is equal to pi h bar divided by E, or I can write it as, because h bar is a reduced Planck's constant and that is equal to h divided by 2 pi, so I can write this also as h divided by twice E, and this quantity phi 0 is known as the flux quantum, a very important quantity, flux quantum. In fact, the primary result that you have is that magnetic flux is an integral multiple of flux quantum. So we see that flux is getting quantized, and physically speaking, this flux quantization is enforced by the screening current that flows in the superconducting ring. So till now we have come across two important facts about a superconductor. Firstly, in a superconductor, the magnetic flux is quantized, and secondly, at low temperature, a superconductor, sometimes referred to as superconducting island as well, is always in the ground state for any given number of particle numbers, and particle can change by 2n, where n is the number of Cooper pairs. Since in most applications related to quantum technology, we are interested in a two-state system, having a single superconducting island is not going to serve the purpose. This problem can be surpassed if another superconducting island, so say if we have just a superconducting island or superconductor, it's not going to serve our purpose, because mostly we are going to confine ourselves to the ground state only, as I have already told you. But if we can put another superconducting island adjacent to the present one, and if the separation between these two superconducting island is on the order of say 1 nanometer, then Cooper pair can tunnel from one island to the another island. Generally, this kind of structures are called Cooper pair box, and the size of a typical Cooper pair box is on the order of micrometer, and the separation between these two superconducting island is, as I said, is on the order of nanometer, not necessarily 1 nanometer. It is on the order of nanometer. This tunneling of Cooper pair is referred to as the Josephson effect. So suppose we have these two superconducting islands, the Cooper pair. I'm just now drawing an enlarged diagram. Separation, I am showing it bigger, but you just take it to be on the order of nanometer only. So Cooper pair, as you know, a Cooper pair has two electrons. This two Cooper pair can tunnel from this upper island to this lower island. In the process, it's going to leave the upper island positively charged and the lower island negatively charged, and this may happen in the other direction as well. In fact, in reality, this excess charge in the respective islands are distributed smoothly on the surface, and if you look at the configuration, it may appear to you that this two superconducting island is now behaving like a capacitor, and because of this reason, say this island, upper island has charge q and the lower island has charge minus q, and this charge is distributed uniformly on the surface of the superconductor, and q is equal to twice the charge of the electron, that is the charge of a Cooper pair. And if there are, say, n number of Cooper pair is getting tunneled from one island to the another, then the total charge is q is equal to 2En. Q is equal to 2En. Overall, the structure, however, remains neutral. This basically says that we can actually assume these two superconducting island to behave like a capacitor, and therefore it can be represented by this capacitance symbol having a effective capacitance, say C. Okay, so this is a capacitance C, and this value of this capacitance depends on the geometry and contains all information about the distribution of charges, and the electrostatic energy of this capacitor or this two superconducting island is given by q square by 2c. This problem can be turned into a quantum mechanical problem if we take K(n) as the basis state, and where this K(n) refers to the many particle ground state. In fact, this is a number state, and this refers to the fact that there are n number of Cooper pairs are there in the ground state. So n refers to Cooper pairs, number of Cooper pairs. It's just like behaving like a number state. N is number of Cooper pairs. And we can define two operators. One operator is the number operator, and which satisfies this eigenvalue equation, and this is the usual eigenvalue equation for the number operator. And we can also define a charge operator. Q cap is equal to twice QE and the number operator. Please note that here I am using the symbol QE to denote the charge of the electron rather than using simply E. However, mostly I am going to stick to my earlier notation of denoting the charge by E only. But in this case, please don't get confused. Here QE refers to the charge of the electron. Then we can express the electrostatic energy by the charging Hamiltonian. So we denote the electrostatic energy as this Hamiltonian H charge is equal to Q square. Q is the charge operator divided by 2C. C is the capacitance. Apart from this term in the total Hamiltonian, we also have a tunneling Hamiltonian that allows us to change the particle numbers between the two islands, and this is given by H tunnel. I'll explain. H tunnel basically tells us how the particle Cooper pairs are exchanged between the two islands. Say n number of Cooper pair is going from one island to the another one, and it increases the one copper pair is say getting tunnel to the other one, increasing the number by 1. Okay, and reverse process also happen. Maybe say now the tunneling is happening say from the lower island to the upper island. So this is what the phenomena is going on. And we also need to have the energy scale, and by convention this energy is called the Josephson energy, denoted by Ej. By convention this energy is written as minus Ej by 2. Ej is the Josephson, this is called the Josephson energy. Josephson energy. By the way, this Hamiltonian we can also write as H tunnel is equal to minus Ej by 2. Oh, I forgot to write the summation sign, because these particle numbers, these Cooper pair numbers can actually change. Not only one Cooper pair may get exchanged between the islands, there may be many. So this summation takes into account, and this n can go from minus infinity to plus infinity. In fact, this n goes from minus infinity to plus infinity refers to the fact that tunneling is happening in the both direction, and any number of Cooper pair may get exchanged from one island to another one. This particular Hamiltonian I can write equivalently in this form also. I can also write it this way also, that what is happening, that in one, when because of this exchange of Cooper pair in one of the island, the Cooper pair is now getting decreased. This Josephson energy Ej depends on the geometry and the material properties of the Cooper pair, or this superconducting set of these superconducting islands, their geometry. So the total Hamiltonian we can write as H is equal to, one part is the charging Hamiltonian, and another one is because of the tunneling. Okay, so this is the total Hamiltonian. Now in a real system, we'd like to tune these energies, and this can be done by putting these superconductors in an external electric field. So if we put these superconductors in an external electric field, suppose the electric field is applied along this direction, and because of the tunneling of Cooper pairs, the charge is smoothly getting distributed on the surface of the two islands like this, and this is going to generate a dipole moment P, and this external electric field or is say EXT. Here this external electric field may be also a voltage also. Now because of the application of this external electric field and the dipole moment that is getting generated due to the coupling, due to Josephson coupling, there is going to be kind of a dipole energy, say E dipole, and that is going to be given by minus P dot E external. This you know from basic physics, and because this dipole moment is proportional to charge, so therefore effectively this dipole energy is proportional to the charge Q. In fact, this particular issue can be captured in the Hamiltonian if we write the charging Hamiltonian in this particular form. If I write this charging Hamiltonian term this way, if I write it as Q minus QZ whole square divided by 2C, where C is the capacitance, and this QZ is termed as the gate charge. QZ is called gate charge. Let me actually expand this particular term to explain it further. Q minus QZ divided by 2C whole square. So this, if I expand, then I get the first term is as usual my charging term, charging energy term, and then I have a term which is proportional to the charge Q, and this is what we required. And then also we also have this term QZ square by 2C, which is a constant term, and this last term is the energy offset term, and it does not contribute much to the physics of the problem. And however, this particular term in the middle, this is of importance to us. This middle term catch the fact that how we are tuning our system by applying an external electric field or a voltage. This gauge charge QZ effectively takes into account the external electric field, and it is proportional to the external electric field. And QZ is the preferred charge we would like to have so that the system can have lower energy. Generally, it is not possible to set QZ is equal to exactly, we cannot set it equal to Q, because Q is quantized. As you know, Q is equal to twice of the charge of the electron into N. But one can have almost this charge, gauge charge QZ can be almost equal to the charge, quantized charge capital Q. So we have our final Hamiltonian in this form. H is equal to Q minus QZ whole square divided by 2C minus EJ by 2 summation n goes from minus infinity to plus infinity, and we have this exchange of particle terms n to n plus 1, okay, plus n to n minus 1. So this is our final Hamiltonian, and this Hamiltonian is known as the Cooper pair box Hamiltonian, and this Hamiltonian is what we are going to discuss now. We are going to analyze it and solve it. Let us try to solve this Hamiltonian, and to do that, let us follow the following steps. First, let us neglect the tunneling Hamiltonian part, and in that case, we are going to left with only the charging part of the Hamiltonian. We can do that assuming that this tunneling Hamiltonian is very weak compared to the charging part of the Hamiltonian. And as you can see from the expression for the charging part of the Hamiltonian, here Q is equal to twice E into the number operator, and in that case it clearly you can see that for every charging operator Q there is a number operator. That means that Q is diagonalized in the K10 basis. Now if we write this as, let me write actually Q as twice QEN, where QE is the electron charge. I prefer to write it this way. Let me write it this way now. And N is the number operator. And QZ, let me denote it by twice QE into NZ, where NZ is a parameter. And then we can write this charging Hamiltonian, or this Hamiltonian, because we are already neglected this tunneling Hamiltonian. So we have Q minus QZ whole square divided by 2C. This I can now write as 4QE square divided by 2C into N minus NZ whole square. This particular term is a constant, and by convention this term is generally denoted as 4EC, where EC is the charging energy constant. Okay, so let me now write this EC is the charging energy constant. Charging energy constant. So we are getting a neat expression for the Hamiltonian in the absence of the tunneling term, that is 4EC N minus NZ whole square. Okay, now let us plot the energy spectrum of this Hamiltonian. The energy corresponding to this Hamiltonian is the charging energy given by ECH is equal to 4EC into N minus NZ whole square. We can plot ECH as a function of the parameter NZ, ECH in the y-axis, and NZ we can have it in the x-axis. Okay, NZ is, as you know, it is associated with the gate charge or the gate voltage or the external electric field. This plotting can give us insight about how the Cooper pair box can be tuned by external voltage or fields. First, let us plot for n is equal to 0. This is going to give the charging energy as ECH is equal to 4 EC NG square, and obviously you can see that this is a parabola. This represents a parabola centered at NG is equal to 0. So this parabola will look like this. It will be this one where NG is equal to 0. Now let us take n is equal to 1. For n is equal to 1, the charging energy ECH is equal to 4 EC NG minus 1 whole square, and this is again a parabola centered at NG is equal to 1. So this would look like this. So it would be centered at 1. So, and it is going to have the same curvature. It would be at 1, and these two parabolas are going to intersect at NG is equal to 1/2. Alright. We can also take n is equal to -1, and which basically means that there are more Cooper pairs at the upper island. This will give us a parabola centered at NG is equal to -1. So we are going to get a plot of this type. This will be like this. Okay, let me draw it properly. We'll have something of this type. In fact, I have to draw it carefully. This particular parabola is going to intersect this parabola here, and right, so this is the parabola. Now this corresponds to n is equal to 1, and this parabola correspond to n is equal to 0, and this blue one correspond to n is equal to -1, and this is your -1 here. Okay, I hope you get the idea. In fact, you can go on plotting it, and you are going to have an array of parabola as you go on plotting for various values of n. You can see that there is crossing of energy levels is happening due to the absence of the tunneling term. Now we are going to switch on the tunneling term, which is a very small term in the tunneling part of the Hamiltonian, that is going to be considered as a perturbation. By the way, in the absence of the tunneling term, we know the ground state of the Cooper pair box as a function of the parameter Nz, right? This already we know. Because ground state is the lowest energy, we always follow the lowest branch in the spectrum. For example, say if Nz, let me write here, if say this parameter Nz, the controlling parameter, if it happens to be lying between -1/2 is here, -1/2 to +1/2, then the preferred charge state is going to be, n is equal to 0. So this is our, for n is equal to 0, this is the ground state, and this represents the gate n is equal to 0. On the other hand, if Nz is lying between say +1/2 to say 3/2, then the preferred charge state, which is the ground state, preferred ground state is going to be this branch. Okay, So in that case, this is going to be n is equal to 1, and so on. Actually, suppose if n is equal to nz is lying between -1 -half to minus say 3/2, then the preferred ground state is going to be, charge state is going to be basically n is equal to -1. So this is what we are going to have. These diagrams are not actually up to the scale, but I hope you are getting the idea what I mean by the ground state. Ground state refers to the lowest branch, and for if nz lies between -3/2 to -1/2, then in that case the preferred charge state or the ground state is equal to, corresponds to the parabola n is equal to -1. That means it represents the ground state n is equal to -1. Okay, now let us switch on the perturbation, that means switch on the tunneling term. If the tunneling term is switched on, because of the fact that this tunneling term is very weak, it's not going to affect the energy spectrum much. Let me first write down the total Hamiltonian when the tunneling term is switched on. That is going to be 4EC n minus nz whole square minus EJ/2 summation n goes from -infinity to +infinity. Here you are having QED-N plus 1 bra n plus n minus 1 QED-N bra n. So this is the tunneling term. Now because of the fact that the charging energy is much higher, that means EC is greater than EJ, in that case this tunneling term is not going to affect much. However, what you can see from the fact that if you look at this tunneling term represents the off-diagonal elements of the Hamiltonian, total Hamiltonian in the K10 basis. And as you have seen from our earlier discussion on two-level atoms, in the case of the two-level atoms, we have seen that the off-diagonal elements in the Hamiltonian, basically what it does is it results in the avoided crossing. So here is also going to be the same thing. When this perturbation is switched on, then these energy levels are no longer going to cross. That means these are going to be avoided. This crossing is going to be avoided. So you are going to have situation like this. In all cases here, these energy levels no longer going to cross. So there is going to be some energy gap is going to be generated. And this is extremely important feature. And this is what is going to be exploited when we are going to, utilize the whole thing to realize a two-level atom or two-state quantum system. So because of the presence of this coupling, the energy levels no longer cross, resulting in the so-called avoided crossing. Let us see how we can realize a two-state quantum system out of this Cooper pair box. To do that, let us focus on the degeneracy point Nz is equal to 1/2. Let us set our external voltage around Nz is equal to 1/2. So Nz is around 1/2, and this is the degeneracy point. In fact, in the absence of the tunneling term, this particular point refers to the crossing of energy at n is equal to 0 and n is equal to 1. Now there may be a slight variation from this point by an amount, say delta nz. So nz can vary from this exact point 1/2 by an amount delta nz if we vary the voltage or the electric field. And in that case, this particular term in the charging energy term, we have this term n minus nz whole square. This term can be expanded as follows. If I just write that it as n minus nz is equal to 1/2 plus delta nz. So this is what I am going to have. If I expand it, then I am going to get n minus 1 half whole square plus delta nz square minus twice delta nz into n minus 1 half. Now because at the degeneracy point nz for nz is equal to 1 half, n can be equal to 0 or n can be equal to 1. So therefore we have n minus nz whole square. I can now write it as 1 by 4. If I put n is equal to 0 or n is equal to 1, then this is what I am going to get, delta nz square plus minus delta nz. Here the plus sign refers to the fact that n is equal to 0 and minus refers to the fact, you can easily see it, minus refers to the fact that n is equal to 1. So in that case the charging energy ECH, I can now write it as 4EC n minus nz, and around this nz is equal to half, the charging energy is going to be EC plus minus 4EC delta nz, and here we are going to neglect this delta nz term because this delta nz is already small, so this delta nz is going to be further small, so therefore we are neglecting this term, and this is what we are going to have for the charging energy for the case when we are confining ourselves around nz is equal to 1 half. That's the degeneracy point. Okay, now also you see that this particular term EC is a constant term, is constant, and this is not going to contribute to anything because in terms of controlling parameter we are having here only delta nz. So this constant term, which is an offset only, we can neglect this, and in that case we can simply retain this second term, that is plus minus 4EC into delta nz. Okay, and now if I take my this charge state n is equal to 0 as 1 0 and get n is equal to 1 as 0 1, okay, then we can write down the charging part of the Hamiltonian, and because that term already you know that this Hamiltonian is diagonal in the QED-N basis, so the terms are going to be, diagonal elements are going to be 4EC delta nz here, and another diagonal term would be minus 4EC delta nz, and off diagonal terms are 0 here. What about the tunneling part? In the case of the tunneling, you know that the tunneling part of the Hamiltonian is given by minus Ez by 2 summation n is equal to minus infinity to plus infinity, and we have here QED-N plus 1 bra n plus n minus 1 bra n. Now because we are focusing ourselves to nz is equal to 1 half, and that means we are, this correspond to the QED state n is equal to 0 and n is equal to 1, because we are just having this 2 as our basis state. So basically this is we are having a two-state system because the basis states are n is equal to 0 and n is equal to 1. So the tunneling term in this basis is going to be equal to minus Ez by 2, and here you are going to have QED-1 bra 0 plus QED-0 bra 1. So therefore in the matrix form I can now write this tunneling Hamiltonian as it has only the off diagonal elements, they are minus Ez by 2, and here you are having minus Ez by 2 and diagonal elements are 0. So therefore the total Hamiltonian when we are confining ourselves to nz is equal to the degeneracy point nz is equal to 1 half, we are getting a 2 by 2 Hamiltonian. That means we are getting a two-state quantum system, and the Hamiltonian is given by, the total Hamiltonian is given by this Hamiltonian, where the off-diagonal elements are 4 EC delta NZ minus here 4 EC delta NZ. Okay, now we can easily apply whatever we have learned about the two-state quantum system. We can immediately find out the energy eigenvalues of this two-state Hamiltonian, and that you can easily work out, and you can find that the energy eigenvalues is going to be given by this expression, square root of Ez square divided by 4 plus 16 EC square delta NZ square. Now we can have a we can make a plot of this energy versus delta NZ, because delta NZ is the controlling parameter. So let us make a plot. So on the x-axis, let me have delta NZ, and on the y-axis let me have E. Now if I have this coupling term, this Josephson coupling, say this perturbation term, suppose Ez is equal to 0, then I have E is equal to simply plus minus, you will have 4 EC delta NZ only. So plus refers to this plot, E is equal to plus, this is going to give me this particular plot, and as you have learned already, seen that this refers to n is equal to 0 state, and on the other hand, for the other one, for minus 1, okay, for E is equal to minus 4 EC delta NZ, so the plot it is going to have a negative slope, and they are going to pass through NZ is equal to 0, so there is going to be a crossing in the absence of the tunneling, and this basically refers to the kth state n is equal to 1. Okay, now when this perturbation is switched on, then there is going to be avoided crossing, and then you are going to get these hyperbolas. One hyperbola would be like this, the other one is going to be like this, and now you see the crossing is now getting avoided, and this gap you can easily make it out. This is going to be simply given by Ez by 2, this energy gap, and this particular point I urge you to show you this, that this represents the superposition state of kth n0. This is going to be asymmetric superposition of kth n is equal to 1 minus n is equal to 0, and this particular point is going to represent the state 1 by superposition state 1 by root 2 symmetric superposition of n is equal to 1 plus n is equal to 0. Please try to show this, otherwise we are going to do it in the problem solving session. Here delta nz is equal to nz minus 1/2, because this two-state system that we are achieving is because of the fact that we are focusing ourselves around the degeneracy point nz is equal to 1/2. Let me stop here for today. In these lectures, we have started discussing about circuit quantum electrodynamics, and in this context, we have started discussing about superconducting qubits such as Cooper pair box, and we have shown that how a Cooper pair box can be manipulated or tuned to get a two-level quantum system. And we'll continue our discussion on circuit quantum electrodynamics in the next lecture as well. So see you in the next lecture. Thank you so much.